Hi everybody, we are starting and we will continue what the subject of both the gas, both the liquid. We have observed some peculiarities for the behavior for the partition function and specifically for the average number of particles at different levels. And today we will try and solve the whole problem of Bose gas. Let's see. Which will be defined as follows. Bose gas. Okay. So we have free particles. Free particles. Particles in a box. Okay. So our box is the same box as we use all the time. Is L by L by L. L to the third equals to V. Okay, are the volume of the box. And the energetic spectrum of all of those particles is similar to the energetic spectrum that we used for the for the fermions. So we have epsilon, and we assume that epsilon is p squared divided by 2m, and if you would write it down in terms of the k vector, so it's h bar squared divided by 2m multiplied by k squared. Great. So this is what we have. And the idea is how we solve it and how we obtain, first of all, the partition function. Afterwards, we would like to write the grand canonical potential. Okay. And afterwards, we would like to write the average number of particles inside the system. Okay. So using the grand canonical ensemble. Now, from what we've seen yesterday, the partition function is a multiplication of all the different possible levels inside the system. So I'm saying, oh, the levels are free particles, right? But there are some specific levels, right? Because we're considering particles inside a box, so the value function of each and single particles, quantum particles, have to zero out at the boundaries. That implies that we will have some sort of quantization or specific standing waves. Here are waves of what? Of the wave function, probability waves, inside this box. Therefore, there are going to be some specific quantization, and this quantization means that we still have some specific discrete set. Okay. This discrete set we do assume that it's almost continuous, and we'll come to this point a little bit later. But for our purposes of writing the partition function, we can say it is a summation over all the possible, or multiplication, I'm sorry, of all the possible levels, energetic levels inside the system, because what is independent is the representation of the levels. And here we're going to have z epsilon. Now, if we assume that we have some sort of a degeneracy inside our system, what I mean by degeneracy, the same degeneracy that we had for fermions. Remember, if I include spin in my system, so I can consider, oh, I have a specific energetic level with energy epsilon, with spin, for example, +1, and I'm going to have this, again, another energetic level with the same energy, but spin downwards. Now, since the energy is independent of the spin, the partition function is going to be exactly the same for two levels, one with spin up, another with spin down, one with spin 0, another with spin 1 or -1, and etc. So in general, we write over here that this is z of epsilon to the power of g0. G0, it's our degeneracy. Okay. If we have particles with one specific spin, 0 for example, because those are bosons, well, we're done. G0 equals to 1, no degeneracy at all. But if we have additional possible spins, G0 is going to be something else. Okay? So the only thing that how degeneracy affects is it's a power. It's a power of any specific level. That's it. Great. So we have this guy. What is psi? Psi we can write down as a general form. It's always the same thing. It is 1 minus 1 over beta log of z. Okay. So if z is a multiplication of those guys, we know that this is minus 1 over beta log of a multiplication of all possible epsilons of z epsilon to the power g0. And this equals to, minus 1 over beta. Here we're going to have G0, and we're going to have a summation of all the possible epsilons, the energies in our system, log of Z epsilon. Okay. Great. Now, the next trick is exactly the same trick as we did in the bimodal, as we did for fermions, is to say, well, I don't care about the summation. I assume that all my energetic levels are close enough, and they are close enough. Okay, we'll see why. And I'm replacing this summation with an integration. So I have minus G0 divided by beta as an integral. Now, what are all my possible energies? Look on this guy, and we're saying, well, all the possible energies are positive. I'm looking only on kinetic energies in my system. I don't have any upper limitation. For any perspective, I don't care if I will have a particle, a boson with huge energy, well, so be it. So the limits of my integration are from 0 to infinity. This comes inside. We have log of z of epsilon, but since we had translated it from summation to integration, we need the density of states. Okay, this density of states is d of epsilon, d epsilon. Yes.
Why you don't use a question פוטנציאל כימי? כאילו, המיו הזה, למה המיו הזה נעלם פתאום?
So where is mu? Mu is here. It's inside the partition function of each and specific state. It is here. It's going to appear what is the epsilon. So this prescription is always the same. It's the same for canonical ensemble, and it's the same for grand canonical ensemble. And actually the same for microcanonical ensemble. Okay, all of this. The difference, do I have mu, do I have different representations, is what are those z epsilons? That's it. Okay? So and we know what z epsilon is. We derived it yesterday. Okay. What was z epsilon? Do you remember? Z epsilon was 1 over 1 minus e to the minus beta epsilon minus mu. This is what we derived for z epsilon. Let's erase this part over here. And the problem becomes technical, right? So what we want to discover, what is the grand canonical potential? What is this guy? Great, the grand canonical potential. We have a formula, general one. The only thing, well, plug inside the logarithm and you will get to something, right? Great. So let's do it. We'll have a lot of algebra today. I know it's just a start, but we're definitely going to have a lot of algebra. Okay, so we plug it inside, and we get psi equals to minus g0 beta, an integration from 0 to infinity, a log of 1 over 1 minus e to the power minus beta epsilon minus mu, d epsilon. D epsilon. Now, what is d epsilon? What is d epsilon? So if you remember, d epsilon, we are treating particles inside a box. Those particles are described by wave functions. Those wave functions describe standing waves. And we know exactly what is the density of states when we have a representation of standing waves. We only need to deal with the k vector. Right? So we have a general formula for this. It is v, the volume. We derived it already for the Drude, for classical waves, but it's exactly the same waves. Right? The solutions for Schrödinger equations are going to be standing waves. I don't care where those standing waves occurred. They can occur because of the phonons, or they can occur because of the solutions to the Schrödinger equations. It doesn't matter. The only thing is the discretization due to the solution to these equations, standing waves. So it's always v divided by 2 pi squared, k squared, dk to d epsilon. Now, for regular waves, in Drude's theory, not Drude, Debye, yeah, Drude is something else. I discussed Drude with you on too many physicists. Okay, so in Debye theory, we have taken this derivative with respect to omega, okay? Because the dispersion relation was k of omega. In the case of particles, or free particles, quantum particles, the interesting quantity is not the omega, it's the energy, right? So the dispersion relation that we use is k of epsilon. This is why we have dk to d epsilon here. Okay? If you want another explanation, see how we got this dk to the epsilon for the fermions. Exactly the same thing. You derive it for Debye and then you use it for everything that relates to standing waves, no matter what's the origin of those standing waves. Okay, so what is k of epsilon? So we know that epsilon equals to h bar k squared divided by 2m. So we have k equals to a square root of 2m epsilon divided by h bar squared. And specifically, dk to the epsilon equals to a square root of 2m divided by h bar squared multiplied by 1/2 epsilon to the power minus 1/2. Okay. And k squared, well, we know what square is. K squared equals to 2m divided by h bar squared multiplied by epsilon. Okay. So we have all the ingredients. We have the epsilon. Okay. We have k squared. We have dk to the epsilon. Okay. Everything is inside over here. We have a logarithm of this guy. So let's substitute everything inside and let's see what happens. So we have psi equals to minus, let's get rid of the minus, right? We have a log of 1 over something, so it's a minus log of this something. So I'm getting rid of this minus sign. So I have g0 divided by beta, an integral from 0 to infinity, log of 1 minus e to the power minus beta epsilon minus mu. I have v divided, so I have 2 pi squared. I have an additional 1/2 over here. So I'll write it down as 2 pi squared. Okay. I have k squared, which is 2m h bar squared, multiplied by square root of 2m h bar squared. So I write it down as 2m divided by h bar squared to the power of 3/2. Okay. And I left only with epsilon multiplied by epsilon to the power minus 1/2. So I have epsilon to the power 1/2 d epsilon. Yes?
Do you שלמעלה למטה ולצדים?
What, this guy?
לא, העליון. בפעם הקודמת שעשינו בדיוק.
Okay, great question, great question. So, the comparison of what is the difference between dBi and whatever I'm taking over here. So for dBi, there were oscillations of waves. Okay, so if I have a wave and the wave is propagating in that direction, I have to take standing waves that are perpendicular to the direction of the wave, and also waves that are transversal in the longitudinal in the direction of the propagation of the wave. So I had three contributions, okay? Three different contributions. For quantum particles, the oscillations are of probabilities. Right? I'm looking, and I don't really have in quantum, as you know, you've been taught solutions of Schrodinger equations. I don't have directionality over here. The only thing that I care are the boundary conditions. Okay? So I don't have those three options. Therefore, I don't have some specific additional prefactors. Okay? So it's a crucial difference. The form stays exactly the same. It's just some prefactor that sits over here for the classical waves, and it's absent for the quantum case. Again, because I don't have directionality. Okay, so we have this guy. Let's make it a little bit nicer. Let's take out everything, whatever we have over here. So we have V divided by 2 pi squared 2n h bar squared 3 halves G0 1 over beta, and I have an integral from 0 to infinity, a log of 1 minus e to the power minus beta epsilon minus mu epsilon 1 half d epsilon. Okay, so it's already nice for us. So I can make this formula a little bit nicer, specifically because I want to emphasize that in a lot of calculations, especially in books, you will see some final solutions that are using representation of Bose distribution or Fermi distribution, which is 1 over 1 plus something. Okay? Actually, it's not needed, but it's the classical representation, or the usual, not classical. Classical, it's obscuring the details over here. So let's massage the situation a little bit more in order to get a nice representation. So let's look just on this integral from 0, so this is psi, from 0 to infinity of log 1 minus e to the power beta epsilon minus mu epsilon to the 1 half d epsilon. And I want to do integration by parts. Okay. Why? Well, because you will see in a second. So integration by parts gives me the following result. I'm saying that this is a derivative of some function, and this is a function. So this is u, and this is v prime. Okay, so the total result is 3 halves, I'm sorry, 2/3, 2/3 of epsilon to the power 3 halves log of 1 minus e to the power minus beta epsilon minus mu between 0 and infinity. Okay. And I have minus an integral from 0 to infinity of 2/3 epsilon to the power 3 halves multiplied by the derivative of this guy, which is 1 over 1 minus e to the power minus beta epsilon minus mu, okay, multiplied by minus e to the power minus beta epsilon minus mu multiplied by minus beta. Okay, d epsilon. Okay, so let's look on this part. When epsilon goes to 0, what is the result of this guy? 0, because epsilon controls everything. So when epsilon goes to 0, at least at this limit. So when epsilon goes to 0, it is 0. When epsilon goes to infinity, what happens? So yeah. So if you do the L'Hopital or Taylor expansion or whatever you like, you see what happens. I have e to the power minus beta epsilon. This is a controlling parameter. So this exponent goes to 0. And the moment that this exponent goes to 0, log goes to 1. And the moment that the log goes to 1, it actually goes to 0, stronger than e to the power 3/2. And all of this guy is simply 0. Okay. Great. Now, when I'm looking on this part, I can say just this part, I can write it down as 1 over e to the power beta epsilon minus mu minus 1. This is what we called Bose distribution. Okay, this is what we call Bose distribution. Moreover, it's also the average number of particles at specific level. Okay, overall, we plug everything inside and we get the following result. So we have psi equals. So we have this integral, which is, let's take out everything that it's not related to epsilon. So we have epsilon to the 3/2 divided by 1 plus, e to the power beta epsilon minus mu minus 1. And we have the epsilon. In front of this integral, this is what we have. Now, we have here 1 over beta. From here we have minus beta. We have another 2 minuses. So overall we have minus. Okay. 2/3 G0 V.
Yeah, how 2 minuses give a minus?
1, 2, 3.
Oh, you have 3 minuses. You said 2.
So here I have 2 minuses and another minus over here. Okay. So minus 2, 3 G0 V. What else? Divided by 2 pi squared. And here I have 2m h bar squared to the power of 3/2. Okay. So this is a nice representation of the grand canonical potential. Great. Now, the moment that we have grand canonical potential, we can derive everything else. So, I just forgot something. It's important. What are the limits of the integral? They go from 0 to infinity. Okay, so great. But I don't really see some problems over here. Maybe there is a problem because, well, this denominator can diverge at some point, but it seems nice, reasonably nice. No. So I have 1 over beta over here and beta from here. They cancel out. This is good. Okay, now the problems, you remember where the problems were, or we suspected that where they come from? Problems could come from the occupation numbers, or the average number of particles at specific energetic level. Okay, so what we are going to do is to derive the average number of particles. Now, as I always tell you, there are 2 ways to write down the average number of particles. Either you start from the partition function and you just use a very simple representation of averages. So it's the number of particles multiplied the probability, or you use a formula. Now, if we already have an integral representation, it's easier in most cases to already use the formula, but it's actually the same amount of work. Okay? Now, the formula that I'm going to use is what is the average number of particles. Okay? So if you remember what is the grand canonical potential. So the grand canonical potential was the average energy minus what we had minus Ts, right? Minus mu n. This n over here, this n over here is the average number of particles. Okay? Any time you're treating the grand canonical potential or any thermodynamical potentials, whatever stands over here are average quantities. So we know from this formula, and if you remember how Legendre transform works, we know that average n is simply minus d psi to d mu. Great. So we have to take this guy and perform a derivative with respect to mu. That's all. Right. So average n equals to, so we have a minus, and minus kills this minus over here. D mu operates where there are nothing that is related to mu in the prefactor. Okay, so the prefactor stays the same. Moreover, I assume that this guy converges and everything is fine with this guy, so I can exchange the order of operations. Okay, I can first perform derivative with respect to mu, and afterwards I will take the integral. Why can I do it? Because I'm a physicist and this is what physicists do. Okay, so 2 to the thirds g0 v divided by 2 pi squared 2 m h bar squared to the power of 3 halves, and here we have an integral. This continues to the second line from 0 to infinity, epsilon to the 3 halves, d to d mu of 1 over e to the power beta epsilon minus mu minus 1 d epsilon. Now, I would like to call all of this prefactor as some sort of a b, just a letter, and focus on whatever happens in my integral. So what's happening inside? I'm taking the derivative, so let's first see what is the derivative. D to d mu, I don't like this marker at all. D to d mu of 1 over e to the power beta epsilon minus mu minus 1. So what I'm getting minus 1 over
e to the
power beta epsilon minus mu minus 1 squared and
e to the power of beta epsilon
minus mu multiplied by minus beta. Great. Looks fine? Looks fine to me. Okay. Okay, so what do I have over here? So in total, n average equals to b, okay, an integral from 0 to infinity of what? Of epsilon to the power 3 halves, and instead of whatever derivative that I have over here, I have e beta to the power of epsilon minus mu divided by e to the power beta epsilon minus mu minus 1 squared d epsilon. Okay. So remember what I like and what I do not like about grand canonical representation and bosons and fermions. I like to represent everything with this Bose distribution or Fermi distribution. I don't like this. Okay? So I will massage this integral a little bit more. Okay? Exactly as we did over here. Okay? Now, how I will massage it, I again perform integration by parts. If you open a book you will have a representation, a final solution that will tell you this is some epsilon to some power multiplied by Bose distribution or Fermi distribution. That's it. There is nothing wrong with this. It's absolutely fine. Okay? But if you open a book, you will have a reference to Fermi distribution or Bose distribution for historical reasons. It's also, people think in this way sometimes, because 1 over, it's coming from Fermi statistics, but because what happens is 1 over this guy, okay, it's the distribution. And we use the property of a Fermi distribution for low temperatures in order to discover what is the Fermi level. You remember I just, at some point I just said, oh, this 1 over something is a theta function. So the same approach goes also for bosons. That's it. Great. So we are going to perform integration by parts. Okay. Beta, I can take it out. Beta is not important. So I can take it out of the integral. And what I have here is, I will call it V prime, and I will call it U. Okay? Now, what happens to this integral without the beta when I perform integration by parts? So first of all, I will have e to the power 3/2 multiplied by, what is the integral? This guy. So I have to look what is the integral, general integral, of e to the power beta epsilon minus mu divided by e to the power beta epsilon minus mu minus 1 squared d epsilon. Okay? So what this guy is, I perform a substitution. What is the substitution? E to the power beta epsilon minus mu minus 1 equals to x. Therefore, dx equals to e to the power beta epsilon minus mu multiplied by beta d epsilon, or e to the power beta epsilon minus mu d epsilon equals 1 over beta dx. Okay, so I have an integral which is an integral of 1 over beta dx 1 over x squared. Okay, so what is the solution of this integral? It is minus 1 over beta 1 over x. And if I'm going to say what is x, x is just e to the power beta epsilon minus mu minus 1. So I have minus 1 over beta multiplied by 1 over e to the power beta epsilon minus mu minus 1. Hooray, hooray, I have something that looks like the Bose distribution for me. So I can plug this guy inside. Minus 1 over beta, 1 over e to the power beta epsilon minus mu minus 1. Okay. And I have minus an integral from 0 to infinity of what? Of the derivative of this guy, which is 3/2 epsilon to the power 1/2 multiplied by whatever stands over here, which is minus 1 over beta 1 over e to the power beta epsilon minus mu minus 1 d epsilon. Okay, now it's important to remember that the first part we have this limits of 0 and infinity. Now when epsilon goes to 0, this part goes to 0 because of the epsilon. When epsilon goes to infinity, this part goes to 0 because of
This one explodes.
yeah, exactly. So we don't need this at all. Right?
Yay.
Okay, so let's look what we left with. We have this part b, Okay, we have the beta that's coming from here, and instead of this integral, we have this guy over here. So let's write down everything. So goes like this. Psi equals to, so we have all of this. It is 2/3 G0 V. It's not psi, it's average n. 2/3 G0 V 2 pi squared 2m divided by h bar squared 3/2 an integral. And inside this integral we have, first of all, we have beta, okay, from this, and we have this guy. So let's take everything that it's not related to epsilon outside of the integral. So what we have minus and minus cancel each other, and we have 3/2 beta, 1 over beta, I'm sorry, 1 over beta, and then have an integral from 0 to infinity of epsilon to 1/2 divided by e to the power beta epsilon minus mu minus 1 d epsilon. Okay, something cancels out. What is this something? 3/2, 2/3, 1 over beta, beta, and the final result, or not so final, is the average n equals to G0 V divided by 2 pi squared 2m h bar squared 3/2 and an integral from 0 to infinity epsilon 1/2 e to the power beta epsilon minus mu minus 1 d epsilon. That's it. So we achieved our goal. We computed the behavior of the ground-canonical potential, and we also computed the behavior of the average number of particles. Can we make it a little bit better? Okay, so I'm looking on this guy, and I don't really understand what happens. Okay. Remember when we had something very similar for fermions, the only difference was that we had some plus over here, and then we used that in the low temperatures. Okay, we can use a theta function, and then we obtained this nice result that the Fermi level is extremely high, and we have this picture that stuff can pile up on top of each other. Okay, so this is what we obtained for fermions. Here, the only difference is this plus or minus. Okay. So what we're going to do next is to look on this and say, let's make this integral or represent this integral in some other fashion. Okay. And what is other fashion? So let's use Taylor representation and other representations in order to explore this integral. Okay, so first of all, what I'm going to do is to say that e to the power beta mu, I will call it zeta. Okay, and it has a name, fugacity, or in Hebrew, plitut. Okay. Now, all of this, I'm going to call by the letter A. So the function that I'm going to explore is the average number of particles equals to A, an integral from 0 to infinity, epsilon to 1/2. Here I'm going to have the fugacity, to the power minus 1, and e to the power beta epsilon minus 1 d epsilon. Okay. Here the big algebra comes around. So fast and tight, and we will fly over very nice representations of integral transformations. Okay, so what I want to do is to start and deal with integral in order to obtain something which at least looks nice and help me something about the problem that I have at hand. Okay, so I rewrite it as a integral from 0 to infinity. I'll take the fugacity out, so we'll have the fugacity, the zeta. It is over here, and we'll have epsilon to 1/2, and I will have e to the power minus beta epsilon, and here I have 1 minus, I'll have the fugacity and e to the power minus beta epsilon, the epsilon. And in a second you will understand why I did this transformation. So nothing wrong over here, I just replace this representation into this representation and take fugacity out. So next thing we will substitute, and what we are going to substitute, we will say that epsilon equals to x squared. So if epsilon equals to x squared, so what we have inside, first of all, d epsilon equals to 2x dx. Okay. Epsilon to 1/2 equals to x. This is why I'm performing the substitution in order to get rid of 1/2 for the epsilon. And e to the power minus beta epsilon equals to e to the power minus beta x squared. Okay. So those are the whole transformations. When epsilon is 0, x is 0. When epsilon is infinity, x is also infinity. Great. So the form that I have left is I'll get the fugacity out of the integral from 0 to infinity, and I have here x e to the power minus beta x squared. I have 2x, I have 1 minus the fugacity e to the power minus beta x squared, and I have dx. Okay. So this is my integral. Okay. I can take 2 out. And I will separate it into 2 different representations. So it equals to the fugacity multiplied by 2, an integral from 0 to infinity. I have 1 over 1 minus the fugacity e to the power minus beta x squared, and I have x squared e to the power minus beta x squared dx. Okay, so what is this guy? What can be handy?
This is the Gaussian integral.
It is, but remember, I don't have a lot of tricks in this class when I'm treating integrals, but the most utilized trick was the Feynman trick, right? So I can say this is d to the beta minus e to the power minus beta x squared. Okay? Fine? Nothing wrong. Okay, now look on this guy. This guy, well, I cannot really do something with it, but I can say it is a sum of a geometric series.
Yeah.
Right? So 1 over 1 minus e to the power minus beta x squared equals to a sum and goes from 0 to infinity of zeta, the fugacity, e to the power minus beta x squared to the power n.
Wait, this is it's like the partition function.
This is a geometric series, or a Taylor expansion, whatever you like to call it. This is a geometric series. Okay. Now I plug back everything, all of this, I put it back inside. So I have 2a fugacity integral from 0 to infinity a sum n goes from 0 to infinity of zeta e to the power minus beta x squared n minus d to d beta of e to the power minus beta x squared dx.
You can take the sum out of the sum.
Because I'm a physicist, I can do a lot of stuff, right? I can take the sum, and I can take the d to d beta. That's what we're going to do. Okay?
Maybe you can take the d to the beta because it multiplies something else.
You'll see in a second. See in a second. Okay, so this is our A. I'm not erasing it because I'm afraid I will forget this A. Yes, any questions?
איך אתה יודע ש-E במינוס בטא X בריבוע בטא בין 0 ל-1?
So what I'm saying is the following. Saying when you look on this guy, okay, and you look on that guy, this is a geometric series. So we had exactly this problem yesterday, okay, and it made and the solution is that I'm saying that there is a constraint on the different values of the chemical potential. It cannot be positive. It has to be negative, okay?
ב-X כאילו יש לנו את ה...
Yes. So if remember this guy. What is this guy? There is beta mu over here. Okay, and the behavior because of the beta mu, so we have, what is this? This is e to the power minus beta epsilon minus mu. And because mu has to be smaller than any given epsilon, I'm fine. Okay, so we have this guy. I'm not erasing this because I will probably forget what is A when I'm finished. So I'm looking on this integral. I can take the summation out of the integration, okay? And I can take also the zeta to the power n out of the integration. Okay. So I have 2a zeta, a sum n goes from 0 to infinity, an integral of zeta to the power n, okay, and I have an integral from 0 to infinity of e to the power minus beta x squared multiplied by n, okay, d to d beta, let's take the minus out so we'll have a minus over here, of e to the power minus beta x squared dx. Okay, let's look just on this guy. What is this? Yeah. So if I'll tell you that it looks almost that all of this is a derivative of something, right? Now, what this something is, so I'm saying the following thing, that e to the power minus beta x squared multiplied by n d to d beta of e to the power minus beta x squared, okay? I want to write it as d to d beta of something. Why I want to do this? Well, you see, e to the minus beta x squared, and I can do integrals of e to the minus beta x squared. I can do this because it's a Gaussian integral. Right, so this is where I'm pointing. Now, it's not exactly Gaussian integral because I have a d to the beta, but if I write it all over here as d to the beta of something, I can take this d to the beta outside of the integral. So what is this? Can I say it is e to the power minus beta x squared multiplied by n plus 1?
Yeah, you can.
Or, okay, let's write it like this.
Yes, you can.
N plus 1. Like this. Yes, so what's the correction?
Take the derivative and you will find out.
So 1 n plus 1, right?
Yes.
Yes?
Yeah.
Yeah. Great. Okay, so let's plug inside of all of this this guy over here. Everybody understand why this equals to that? I have to take the derivative of this guy. First I take n plus 1 down, and I have whatever I have inside to the power of n. This is why I have n over here, because I started with n plus 1. And then I have to take their inner derivative, which is the derivative of e to the power minus beta x squared. Okay. So I plug everything inside, and n average equals to minus 2a a summation n goes from 0 to infinity zeta to the power n plus 1. I just, instead of writing zeta to the power n, I write this as zeta to the power n plus 1. 1 over n plus 1 d to d beta, an integral from 0 to infinity of whatever is left inside. And what is left inside? E to the power minus beta x squared n plus 1 dx.
This integral is a known integral.
Of course, and you all know it, I'm sure. What is the integral of e to the power minus
Square root of
Wait,
pi
but
divided by.
the
you need
limits,
to take 1/2
but the
because
limits
something
it
happens.
doesn't. But the limits it's a little bit convoluted because the limits are from 0 to infinity.
Yes, and what's-
No, minus infinity to infinity.
Oh, okay. So you make a simple transformation. So you know the following: an integral from minus infinity to infinity of e minus whatever v a x squared dx equals to square root of pi divided by a. And if I'll take it from 0 to infinity, because it's
You need to simply.
what is the function?
It's a.
Just take factor of 1/2. It's enough.
So
Even.
it's an even function. They're odd function and even function. Because that's an even function, so we know that the integral from 0 to infinity of e to the power a x squared dx equals to 1/2 square root of pi divided by a. Okay? This is why I wanted to use this representation, and this is why I substituted over here, at some point, epsilon equals to x squared. Because there are not a lot of stuff that we can compute, but we can compute things that are related to harmonic potential, and the Gaussian integral, it's something that relies on harmonic potential. You will learn it maybe someday in field theory. Anyhow, we know this guy. So we have n equals to minus 2a as sum n goes from 0 to infinity, fugacity to the power n plus 1, 1 over n plus 1, and multiplied 1/2 d to d beta, d to d beta, and here we have 1/2 square root of pi
Divided by
beta
n plus 1.
beta n plus 1. Okay. Now, d to d beta of 1 over square root of beta equals to minus 1/2 1 beta to the power minus 3/2. And now it's time to write everything down. So, n equals to let's see. So first of all, I have minus 2 1/2. I can get rid of this. So I have a.
No, you have another. It's a half. You have another half.
I know. I just cancels out.
No, you have 2 halves. one from the differential and one from the...
Okay, great. So I have A divided by 2. Thank you. A divided by 2. And I have beta and square root of pi. Beta to the power minus 3/2. What else do I have over here? Summation. N goes from 0 to infinity. Zeta to the power n plus 1. 1 over n plus 1 to the power of 3/2. Now, you can say, Stas, can we do something else? What physicists and mathematicians do when they discover a power law expression? In a sense, this is some sort of Taylor expression, right? So I have a coefficients and I have powers of a given function. Right? So usually physicists say, oh, we will define a new function. And we have a Taylor expression for this function. And this is enough for everything. Right? So this function called f alpha of z has a name. It's a polylogarithmic function. We have its power series expression for this. It equals to a summation. R goes from 1 to infinity. Z to the power r. 1 over r to the power alpha. And no, I cannot write this function in a simpler form. This is the guy that I have. Okay. So finally, I can explore the behavior of this function. Right? But this is the function. So finally, I have for n the following expression. What we have over here. So we have G0 V divided by 2 pi squared. We have square root of pi, and we have 2m divided by h bar squared to the power of 3/2. Okay. And I have k Boltzmann t to the power of 3/2, right? Because beta is 1 over k Boltzmann t. Okay. And I have this polylogarithmic function of 3/2 because the alpha over here is the power of whatever stands in this place. Now notice that I have here a summation from 0. But all the n's are starting, well, when n equals 0, it's the first power. Okay? So it's exactly this thing over here. So I have f of 3/2 of the fugacity. Okay? And that's it. Now, there is a nicer way to write it down. Where is this? I'll write it down as n equals to G0V divided by lambda t to the third power f3/2 of fugacity. And from this expression, we know that 1 over lambda t to the third power equals to square root of pi, 2 divided by 2 pi squared, 2m divided by h bar squared, 3/2 k Boltzmann t with 3/2. Okay? I just pushed everything, it's ugly stuff, here, and lambda t has a name, is the thermal wavelength. Okay? It's just nicer to write it like this. Okay.
Got units of distance?
Almost. Not exactly, but almost, yes. Wavelength. So you have this. This is why it's thermal, and you have over here. So if you think of it, you can. This is joules and this is joules because they enter together, and everything cancels out by the terms of units. Anyhow, so this is the expression. You can say, well, Stas, yes, you managed to write it down nicely, mainly because you pushed everything that's related to the temperature into one constant, this lambda t. But you have this function which, well, it's not a nice function. I don't really understand how this function works. Okay? But luckily for us and for physicists, mathematicians explore this function. Okay? They explore the behavior of f to the 3/2. And what they found out is that this function behaves a little bit awkwardly. Okay. So let's look what happens to this function. F. So nothing bad happens over here. If you think about it, G0 is the degeneracy. Well, it depends on what kinds of particles I'm treating. V is the volume. Okay, depends on your system. Lambda t, well, there are some specific, so the mass of your particles, h bar is a constant, pi is usually constant, k Boltzmann is a constant, and temperature you can control. Okay? Nothing really bad happens at 4 lambda t. The only thing that can go weird is this guy. Now, remember what we've done for fermions, and I will tell you in a second how this function behaves. But for fermions, we did the following trick. We explored the behavior of the average number of particles, okay, for a given temperature and for given mu. When we found the solution, we turned everything upside down. We said, oh, let's say that the average number of particles is constant because I have a specific system. The number of bosons, whatever, inside is constant, I can fix it. So when I'm modifying temperature and I'm keeping and constant, what has to happen is that mu is going to be different each time. Okay? I cannot start with this, but whenever I finish, I can say, let's fix n, modify t, therefore mu is going to be different. So this becomes not a parameter, but a variable. The fugacity becomes a variable. Specifically, the chemical potential mu is now a variable, and I know that it's limited. It cannot be 0, okay? Or the lowest level in my system. Okay? So we want to see how this guy behaves. So you can open Mathematica, Wolfram, and you plot this function, and I have f of 3/2 of zeta. And here I have zeta. And this function goes linearly when it comes to a specific point exactly when fugacity equals to 1 and the value of this point is 2.61. 2.61 to whatever. So what we see is that we have an upper limit of this function. It's not the function explodes, well, it's simply not defined for any fugacity larger than 1. Why? We had a sum over there. Remember the sum that we used a geometric series in order to describe it? The sum was not defined for mu greater than 0. Fugacity, it is e to the power beta mu. The moment that mu becomes larger than 0, fugacity is larger than 1, everything exploded over there, something really bad happens. Okay. We've already seen this yesterday. This is an average number of particles exploded, but it's not exploding for the whole system. It has an upper limit. Great. Mu cannot be larger than 0, which is fine. And this function, well, its derivative has something, it happens something very nasty to this, to the derivative of this function. But the function itself is limited. And it has an upper limit, and this is 2.61. So, if I'm looking on this, I'm saying, all right, so I know that f of 3/2 of zeta is less than or equal to 2.612. This is from one side. On the other side, I know from here that it is n divided by v, which is what? Which is the density of the number of particles that we have, multiplied by lambda t to the third power divided by g0. Okay. So the expression that we obtain is that n, which is now, I said this number, divided by the volume, multiplied by lambda t to the third divided by g0 is equals or smaller than 2.612. This is what we get for the polylogarithm number. Some number. The point that it's constant. A finite number. Now when I'm looking on this, I'm saying this is ridiculous. Why it's ridiculous? Well, look on the lambda t. Lambda t, I can make it whatever I like. I control the temperature. Okay, so I'll set the temperature. And then, well, I can make the density whatever I want. Right? So, why this guy have to be limited? So this is the problem over here. When I'm looking on this, I'm saying, that's fine. This is a limited guy. But I can control n, I can control v, I can control the temperature, and this whole representation says, well, no, there is a limit to the number of particles, or the limit of the volume, or the limit of the temperature. Fine, there is a zero bound for the temperature.
Because of the quantum mechanics of the problem, there is limited number of energy the system can uphold, so there is limited number of particles.
No, I can control particles. I can push particles inside. And where the quantum stuff got from. So we use quantum mechanics in order to derive the density of the energies. Something went bad. So you understand the problem? The problem is I can control this, I can do it whatever I want. I control V, I can do whatever I want. I can modify my temperature. And still, out of everything what we've done today for the last an hour and a quarter, something went wrong. Why? Because I wouldn't expect that those parameters or those variables will be limited. Yes?
חישבנו עכשיו את כאילו מספר החלקיקים הממוצע במערכת או ברמה מסוימת?
In all the system, n average is the total number of particles inside the system. Okay, so I prepare my system, I close my walls and then say nobody escapes. Nobody.
אז מה המשמעות של ממוצע של החלקיקים?
So remember, this is the trick. I use the general, the grand canonical ensemble. I calculate everything, and then I say, well, let's fix this now. And mu is
Maybe
the variable that is modified. Okay? That's the same trick that we use for fermions, and it worked perfectly well.
אבל אז מספר החלקיקים כן משתנה?
No, eventually. I calculate everything for a general number. Then I say, let's fix this general number and say and see what happens. So what happens is that mu can be modified from -infinity to 0. Okay, I can get any mu, which is fine. Give me n, give me the temperature for a fixed volume. Okay, and I will find what is the what is I'm sorry, what is the chemical potential. Out of this number, I get something very weird. I cannot get a chemical potential. So you can say, oh, let's make this number on the left-hand side. It's not limited to 2.612. Let's make this number 3. What is the chemical potential for 3? There is nothing. This function cannot get a value of 3. If this function would explode at 1, get a divergency, everything would be fine. Okay? Because I can get actually any number. There is no limitations. The problem with this Pauli logarithm is that it's limited. It cannot be over here. It's forbidden. I did something wrong. Something went wrong on the way. Okay? So you understand the problem? Yeah. We did everything kosher, and eventually we got something which is, no. What went wrong? What do you think that can get wrong? So the one answer is, well, Stas, you're a physicist, you should better give this problem to mathematicians. You made a lot of approximations on the way, right? We did a lot of approximations in computing this integral.
Yes.
Yes. Okay. So let's assume that it's coming from those approximations. What were two or one major assumption that I did in the first place? I assume that the energy levels are continuous, right? Remember, this is what I started with. There are continuous levels, although the levels are not continuous, right? What are the levels? The levels are discrete levels based on the solution of Schrödinger equation of a particle inside the box. There are no interactions, but the box basically says that we'll have standing wave solutions, and there are some specific numbers, and x and y and z. Okay, so if I'll write it down, what are the solutions? What are the solutions? So generally, it is n x, n y, and n z. And we have it always p squared divided by 2m. But it is h squared divided by 2, 8 m v to the power of 2/3 and x squared plus n y squared plus n z squared. Right. Where it's coming from? It's coming from, well, what exactly the the impulse is. And I know that the solution for Ex, it is h divided by 2m. I'm sorry, it's h 1 over lambda x. Okay. And Py, it is h divided by lambda y. And Pz is h divided by lambda z. Okay. Great. So this is my discrete spectrum. I should go, okay, plug here everything and play with nx and ny and nz. Okay. Now the lowest energy that I have is when I have exactly one particle. Right? The lowest energy that I have is just one single particle, or two particles. I can have an x1 and y1 and an z1. So if we take a system where something indeed gets wrong, peculiar things happen, which is helium. Okay. So for helium 4, okay, He4, we have the mass is approximately 6.6 multiplied by 10 to the power minus 7 kilograms.
You're taking it 4 in order to be bosons?
Yes. Well, let's assume that I first observed something which is bad. And then I say, well, where it went bad. But 4 here is for bosons. Right? So I have 4 electrons, and the total spin of this particle is integer. Okay? The moment I have a spin that is integer, I'm fine. I'm treating bosons. So we take, this is the mass, and we take the volume okay, to be approximately 1 liter. So 10 to the power minus 3 cubic meters. Okay. I plug it inside. I plug everything inside. Plug those parameters into this formula, and I want to calculate E211 minus E111. Okay? So what is the first excited state above the ground level? And when I plug everything inside, I will get 2.5 multiplied by 10 to the minus 37 joules. Okay. The levels are highly packed together, extremely highly packed together. Okay. So if I'm thinking about it in terms of temperatures, so E211 minus epsilon 11 divided by K Boltzmann, it's approximately 2 multiplied by 10 to the minus 14 Kelvin. So any temperature can raise the particle from the lowest level to the first excited level. Okay? Nobody can achieve, well, I don't think that we even today can achieve temperatures as close to 0 as to 10 to the minus 14 kelvins. Okay? Insane low temperature. So the levels are extremely packed. Okay? So I had this assumption that, well, yeah, you have specific levels. This is why you can sum. And I say, well, they are extremely packed together. Okay, so instead of a lot of discrete levels, I used a continuous representation. There is nothing wrong with that. It's extremely small differences. So the approximation, very well. So the moment that you test Stas, something will get weird when you go to extremely low temperatures. Oh, maybe, but I don't care. Because nobody going actually to those temperatures. I don't care about 10 to the minus 14 kelvins. Okay, so although their boost sums or whatever in order to represent the integral are perfectly fine. Okay, so
This approximation was correct.
it's fine. It looks fine. Okay, so I use this approximation.
But
What?
to check the ground state, I mean 110 and 100.
It's going to be even smaller. It's going to be even smaller because you see you have this prefactor. So this prefactor can be what? 3, 4, 5, 6. This is the guy that kills you. Okay? This is why everything is so small. Okay. It's the mass and the h and whatever. And the v. What else have I done which can be wrong? Okay. So I use the continuous representation. Okay? Now, we usually don't think about it because we are physicists, right? But what we exactly did. So the continuous representation was fine. We had epsilon, and we said that, well, we had some function of epsilon, and we took an integral over this function, right? We had some f of epsilon, okay, which did something, okay, and we computed. Remember, all the computation was what is some specific integral over there. The specific integral, we say there was epsilon to the power 1/2 divided by e to the beta epsilon minus mu minus 1. Okay. Nothing bad for any non-zero mu. Okay, and you just compute whatever stands over here. And we said, well, if we look on the spectrum was discrete. The spectrum was discrete, but all those levels are very dense. So it's not really bad to make this approximation. What else can get wrong with this approximation of something which is finite by which is a sum, but we do an integral? The spectrum is okay, but the function itself can be something different, right? So what is the function? The function is not continuous function, right? So what actually being there are specific values for specific epsilons. Okay? So we had one value for this guy, another value for that guy, another value for this guy, etc., etc., etc. So we had a set of points, okay? And instead of counting all those points, we approximated everything by an integral. Now, what mathematicians teach us in the first class of calculus, or the second, is, well, you basically replace the summation by some Darboux sums, and you have those specific quadrangles, and you count the sum. But this works only when those guys can be very small, and also the differences between the sufficiently close values of the functions also small. Right? What will happen if I erase one guy from here? Nothing, because the value, okay, value which I erased, so let's assume it's a small area over here. The moment that the width of this rectangle becomes extremely small, the area of the rectangle goes to 0. So the contribution of any specific point in the integral is basically negligible. Unless the value of the function is extremely high at this point. Okay? So you cannot approximate a sum, even by an integral, the moment that you have huge differences between different values of the summands. Okay? And this can be a problem. Okay? And this can be a problem because in this case, you cannot say, well, there is a specific point that it's something. The moment that you have a huge difference between the values of the function in specific range of epsilons, and this specific point stands out, okay, then you cannot approximate this integral by a sum. You have to take specific care, special care of this function, of this point over there. Okay?
We have this point in epsilon equals to mu.
A specific point, when epsilon goes to mu, the value of this guy exploded, right? The value of this guy exploded. And the moment that the value of this guy exploded, okay, somewhere in the sums, you cannot take it out as granted. It's not an integral. You have one specific point where this guy can diverge, and the moment that they have extreme divergence, think about it, I have a delta function at some point, and when I'm performing an integral, I forgot about this delta function. The integral is not going to be correct. Can something like that happen over here? Okay, and if I calculate the following thing, so here I calculate the differences between the levels. Okay, now what is important is this epsilon minus mu. How far away epsilon minus mu from each other? So if I would do the same trick, and I will calculate epsilon 1 1 minus mu divided by k Boltzmann. In the limit when mu goes to 0, I will obtain something like 10 to the minus 21 Kelvin. Okay, but if I'll calculate epsilon 211 minus mu divided by k Boltzmann, I will obtain something that goes as 10 to the minus 14 kelvins. Okay. So if you remember, n, the average occupation number for each specific level, n of epsilon, equals to 1 over e to the power beta epsilon minus mu minus 1. So if we'll take n to the power 1 1 and divided it by n to 1 1 1, using those guys over here, we'll get approximately 10 to the 7. 10 to the minus 7. There is a huge drop. So think about it. we're shifting extremely small amount across epsilon.
No.
Specifically with
Not 10 to the minus 7. You divide the 10 to the minus 1 is much smaller.
10 to the 10 to the minus 1 is much smaller.
10 to the minus 1 is 10.
My mistake. This is minus 21, this is 14. Because what stands inside this guy, this only thing that's important is whatever epsilon minus mu. So what we have a function that is a sum, and we looked on this sum and we approximated everything as if it's an integral. And this is fine because the differences between different epsilons are very small. But the problem was that exactly when epsilon is 0, over here, the lowest possible energy that we can have, there was a huge drop-off. Okay? It's not a simple continuous function. It goes something like this, and then like a delta function. It's 7 orders of magnitude. The difference between the occupation of the lowest, the ground state, and the next excited level. Okay? This is not approximated by the integral. So this is why we had a specific problem with our result. Because what we computed the area below the curve. And this area is limited. It's smaller than specific number. 2.612 multiplied by some constant a. There's always a limit to the area under the plot of this function. But we neglected whatever happens at the ground state. And what actually starts to happen at ground state, that the particles start to pile up on this specific level. Okay? So think about it. When I want to look on n epsilon, I have 1 minus e, 1 over e to the power beta epsilon minus mu, minus 1. I take the lowest epsilon that I have inside my system. I change my temperature. As a function of this temperature, mu becomes larger and larger and larger because my total number of particles is fixed. So mu is changing with the temperature. Mu becomes larger. At some point, mu gets too close to epsilon. When it gets too close to epsilon, I cannot simply neglect the behavior of this value of the function. It's not negligible. It's not approximated by an integral. It's nothing. I have to treat it differently than everything else. Okay? Now you can say, yeah, Stas, it's fine, but what will happen to the next level? So what happens to the next level? It's protected by the ground state. The particles will accumulate, so mu goes to epsilon. Because there is a possible divergence over here, and epsilon, it's always smaller than the average number of particles. But as mu goes closer and closer and closer to epsilon, and epsilon becomes comparable to the total number of particles inside my system. This phenomena called the condensation. So what will happen is that for specific mu, all the particles are going to be at the lowest energetic level. Because n epsilon, for some specific mu, can be exactly equal to the total number of particles. They will prefer to sit in the lowest level and not on the first excited or a second excited. They are protected because the epsilon on the next levels is higher. Okay. This behavior called the condensation. Condensation is you have huge number of particles. What is the number of particles? On the order of 10 to the power 22. We have an Avogadro number of particles inside the system. We reduce the temperature. The chemical potential rises up. The chemical potential rises up. More and more particles prefer to sit at the lowest level. At some point, the number of particles that sit at this microscopic level, think about it, there are almost continuous levels. but the number of particles that can sit at the lowest level is proportional to the total number of particles that we have inside. And this breaks everything. And this is where condensation occurs. So you look on the system and you cannot say, well, it's continuous spectrum, particles can be whatever they like. Okay? There is no preference to a one specific level, you just need to compute the energy and that's it. No, what starts to happen is that you have a disproportional or huge number of particles that are sitting exactly at the ground state. The system condenses on this level. And very nice physics starts to occur. I will describe a little bit what happens exactly at this transition. But if you heard about superfluidity, if you heard about superconductivity, what happens over there is that all the system or huge number of particles are sitting exactly at the same state and they behave described exactly by one wave function. And then, for example, system don't have friction at all. Right? You can have an electric current without any resistivity. The resistivity will go to zero. You can have a fluid like this helium that will flow and it will be frictionless. It can go over some specific barriers and etc. etc. Why? Because you will have huge number of particles. You will have this condensate that will sit exactly at the lowest level. Why it happens? Because you are bosons. And because you are bosons, you have this boson distribution and the lowest state can be approximately equal to the total number of particles that you have inside. How exactly it works mathematically, I will describe to you on Thursday. Thank you.